the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for linear algebra students who are going through the matrix of a linear transformation. You should have just finished the topics on onto mappings and one-to-one mappings, because this topic that we're going to be talking about in this video requires that knowledge. Just as a brief reminder, a mapping is said to be onto if every vector in the codomain is born of, or in other words, the image of, at least one vector in the domain. And a mapping is said to be one-to-one if each vector in the codomain is the image of at most one vector in the domain. Now, if you had combined those two, it leads to a very beautiful picture. And that picture is this guy right here. It's one-to-one and onto. That is, the range matches the codomain. In other words, if you have a vector in the codomain, it is mapped to, or in other words, the image of a vector in the domain. For an example, if I just randomly pick a vector, this guy right here, and it's in the codomain, which normally does not mean it's necessarily in the range of your transformation. But now, if the mapping is onto, we happen to know that vector that's in the codomain is actually in the range of our transformation. Let's call that vector B. That vector B gets mapped to from an element in the domain of the transformation. But not only that, being one-to-one means that that vector B is the image of only one such vector in the domain. In other words, if you map backwards, it leads back to only that vector U and no other vector. So this is the ideal situation. Every element in the domain leads to an element in the codomain, and every element in the codomain leads back to a single element in the domain. And that statement about at most when it comes to one-to-one is not needed, because remember, a mapping is one-to-one if each vector in the codomain is the image of at most one vector in the domain. But because we're saying it's also onto, then the codomain is actually the range. That is, every vector in the codomain is the image of a vector in the domain. All right, so back to the task at hand: transformations, existence, and uniqueness of solutions. Theorem 12 sounds like an important theorem, doesn't it? Well, it is important. I still glue this theorem into other theorems in the long run to make more sense of its placement in the course. But let's go ahead and read the theorem and then make sense of what's going on. Let T, which maps Rn to Rm, be a linear transformation. That linear part is very important. And let A be the standard matrix for that transformation. Then T maps Rn onto Rm, that is, the codomain and the range match up, if and only if the columns of A span Rm. That is, the columns of A can build Rm. And that's an if and only if. So if somebody comes along and says, hey, guess what? The columns of A can build Rm, then we know that the transformation built from that standard matrix maps Rn onto Rm. The second part of this theorem says T is one-to-one. That is, each vector in the codomain of the transformation leads back to, or is the image of, at most one vector from the domain, if and only if the columns of A are linearly independent. So because it's an if and only if, it goes both ways. And I've said this repeatedly, but it is true. This is where this course, linear algebra, continues to get more and more complex with theorems that kind of step on the toes of other theorems. They all kind of start sounding alike, and it becomes very difficult to really kind of pull through the noise here and figure out which ones are important and which ones get used infrequently. Let's go ahead and prove this theorem, and we'll start with part A. And instead of going forward, in other words, instead of saying, let's assume that T maps Rn onto Rm, let's actually start at the back end here, and we're going to build some if and only if statements. The reason why I'm choosing to start at the back end is because we have a lot of theorems at our disposal that really talk about column spanning things and stuff like that. So it'd be really nice to head back to those theorems to figure out if we can use any of them here. So here's our critical theorem list. I'm going to only look for numbered theorems. Honestly, if you've noticed, I rarely actually have accessed or referenced non-numbered theorems. It does happen, but not that often. And so therefore it makes more sense to really focus on the numbered theorems. Now remember what we're trying to assume here, that the columns of A span Rm. And that very important theorem 4 right there is the winner. The columns of A span Rm. This is going to be a bunch of if and only ifs. Specifically, that the matrix equation Ax equals B has a solution for every single B in Rm. And that's going to be incredibly useful. So let's go ahead and hop back and just state that. There we have it. The left-hand side is true. The columns of A span Rm if and only if by theorem 4, Ax equals B has a solution for every single B in Rm. Remember, Rm is the codomain of our mapping. So saying that Ax equals B has a solution for every single B in Rm is exactly the same as saying, every vector in Rm is just the image of some vector in Rn. And that is true if and only if the linear transformation is onto. So that's a chain of if and only ifs. I actually didn't have to prove it in both directions. Now let's go ahead and do part B. And this one I will go ahead and actually I'm going to do the same thing. I'm going to start on the back end here. So let's assume that the columns of A are linearly independent. Again, looking through our old theorems, because I want to show that T is going to be 1 to 1, and we know from the previous theorem from last video that T is 1 to 1 if and only if T of X equals 0 only has the trivial solution, I want to look for a theorem centering on Ax equals 0, or the homogeneous equation. And that would be my labeled theorem 0. So let's take a look at that. Here we are in our critical theorem list, and I don't see anything that links linear independence of the columns of A here yet, but if I turn the page, you can see it right here. The columns of A in the homogeneous equation Ax equals 0 are linearly independent. Well, we happen to know, we've made the assumption, that the columns of A are linearly independent. So we're going to use this, and that is an equivalent statement to saying that A has a pivot in each column, for example, but that's not what I'm going to use. Instead, I'll use the fact that this means the homogeneous equation Ax equals 0 only has the trivial solution. Those are an if and only if, so they're linked hand to hand. They're basically the same statements. So there we have it. The columns of A are linearly independent if and only if by theorem 0, the homogeneous equation Ax equals 0 has only the trivial solution. Remember, A is the standard matrix for this transformation. And hopping back to that theorem that we proved in the last video, if T of X equals 0 has only the trivial solution, well, that's true if and only if T is 1 to 1. And remember, T of X equals 0 has the same solution set as Ax equals 0 because A is the standard matrix for our transformation T. So Ax equals 0 only has a trivial solution, means T of X equals 0 only has a trivial solution, which means T is 1 to 1. And I put that intermediate step in there just so that you could see it. But then by theorem 11, T must be 1 to 1. And again, that's exactly what we wanted to prove with part B. So this is how you can prove an if and only if you have a chain of if and only ifs to support you. And that's going to be more common as we move forward in linear algebra, as you link a bunch of stuff that are equivalent statements. They're all saying the same thing, just in different ways. So from this point forward, I have expanded theorem 4 because I don't want to have theorems 11, 12, 37, 86 or something like that. I'm just linking together concepts that are like kind concept, so we don't have to say, oh, and then by theorem 12 and so on and so forth. So theorem 4 is now expanded. We already had these first 4 statements, but those first 4 statements, any of them, are actually equivalent to this 5th statement. And notice I changed the language at the top. The following statements are logically equivalent given a constant coefficient matrix A, which is a standard matrix for the linear transformation T. And likewise, we have one for theorem 0. This guy right here, again, the first 1, 2, 3, 4 statements we kind of had previously, and now we're adding this 5th statement. This is theorem 0, which is definitely not in the textbook that I use, but I call it theorem 0 because, again, it's about the homogeneous equation. So why not, right? So let's go ahead and do an example. And this example is kind of a low-level example, I apologize, but it's just something so that you kind of know how to use the language that we've developed. Let T be a linear transformation with A its standard matrix. Complete the following statement to make it true. T is 1-to-1 if and only if A has blank pivot columns. It'll take a while for you to get used to, but the 1-to-1 condition is a uniqueness condition, and onto is an existence condition. Let me actually state that up above. And when you're talking about existence of solutions, now remember, AX equals 0. This is kind of an easy way to remember it. AX equals 0 always has a solution. There's not even a question to whether or not AX equals 0 has a solution that exists. It does, X equals 0. So AX equals 0 is not about existence, it's about uniqueness. Now, when I say AX equals 0 is about uniqueness, I mean the theorems that center around AX equals 0 center around uniqueness of solutions, versus AX equals B. Theorems that center around AX equals B generally center around the existence of solutions to the non-homogeneous equation. Again, to remember which one is about existence and uniqueness, it's kind of easier to note that existence versus uniqueness. I know that I am not concerned with the existence of a solution for AX equals 0 because the reality is it always has a solution. So that's not even a question. So immediately I know any existence questions are going to center around AX equals B. Immediately, those two are glued together. So it must therefore be vacuously true that uniqueness questions are centered around AX equals 0. The hard part is knowing which one is linked to onto versus 1-to-1. But actually, it's not so difficult because 1-to-1 means that every single vector in the codomain can only be the image of at most one vector in the domain. That is, if there is a solution to an equation, Tx equals whatever, that solution's going to be unique. So again, that's why 1-to-1 is linked to uniqueness, and uniqueness is linked to AX equals 0 because AX equals 0, we're not even concerned about existence. It's trivial. Literally, it's the trivial solution. So that all being said, when I say T is 1-to-1, I know immediately, okay, 1-to-1, that's all about the uniqueness question. And then I think to myself, okay, so am I looking at something to deal with AX equals 0, or am I looking at something to deal with AX equals B? Well, let's see. The other possibility, rather than just uniqueness, is existence. Well, there's no reason for existence to be a concern when you have AX equals 0. So existence must be concerned with AX equals B, and uniqueness must be concerned with AX equals 0. The reason why I say it that way is because that's how I know which theorem I'm going to look at. I'm going to look at my theorem 0 to see if that can help out, versus theorem 4, which is everything to deal with AX equals B. So let's take a look at theorem 0. And remember, we're going to say T is 1-to-1 if and only if A has blank pivot columns. Well, let's take a look at theorem 0. Well, here is theorem 0 right here. Homogeneous equation AX equals 0 only has trivial solutions. Let's see, it doesn't have free variables. Let's flip the page. It has a pivot in each column. Oh, and the columns of A are linearly independent. But wait a second. I just read something there. A has a pivot, oh, in each column. Well, that's what we were concerned with. Our statement was T is 1-to-1 if and only if A has blank pivot columns. Well, let's take a look at that again. So I want to somehow use the fact that A has some number of pivot columns. I need to make a claim. Well, the number of columns that A has, A is an M by N matrix. And we know that because A maps Rn into Rm. That is, I have to multiply A by a vector that's in Rn. Well, if this vector is in Rn, that means A has N columns, which means it has M rows. If it has the N columns, it has N rows. So I know that every column, I'm claiming that, sorry, I shouldn't say I know, I should say I claim that all columns must be pivot columns. That is, it has N pivot columns. But how do I justify that? How do I prove that or tell somebody, well, this is why that's true? Well, if we're going to follow the theorems in the order in which we prove them, our transformation is 1-to-1 if and only if the columns of A are linearly independent by theorem 12. And remember, I included the statement in my brand new theorem 0. The linear transformation T is 1-to-1 if and only if the columns are linearly independent. But now that I glued this into my theorem 0, I could have skipped that and I could have just gone to, well, that's true if and only if A has a pivot in each column. But because they didn't formally glue these together, and I am, I'll just go ahead and follow probably what an author would want me to do, which is start here by theorem 12. That's going to be true, that the columns of A are linearly independent. And by theorem 0, A has a pivot in each column. And there you go. Those are the great, strong justifications. Now, again, at this point, you do need to have your theorems kind of by your side as you're doing any type of work, homework, or whatever, because it can get daunting to remember this stuff. So I highly recommend that. And to kind of support that statement, here is my end of chapter critical theorem list. This is not exhaustive, but it's kind of the list that's critical, right? So I've really pared this down. There are some very important statements here, like the matrix equation AX equals B has a solution if and only if B is a linear combination of the columns of A, right? There's just no way I can get away without claiming that. A homogeneous linear system is always consistent. That's kind of important. The superposition principle for transformations happens a lot, so it's nice to have that. And then there's that famous theorem 0. Notice I didn't put in theorem 1, but I skipped right to theorem 2, which is the existence and uniqueness of solutions theorem. And then theorem 4, which is all the stuff about AX equals B, which is the existence theorem, if you will. And remember, the uniqueness theorem, in a way, is theorem 0. Even though we do have theorem 2 called the existence and uniqueness of solutions to linear systems theorem. But theorems 0 and 4 really are centered around uniqueness and existence, respectively. And then theorem 6 is also super important, that the solution to the non-homogeneous matrix equation also will include the solution to the homogeneous system as well. Don't think that I don't have any other theorems listed, they're just on the next page. But they do get pared down. I don't have 10, 11, or 12 here because 11 and 12 got bled into theorems 4 and 0 respectively. But here are the 3 extra theorems, and actually theorem 9 is kind of a caveat. So there are some of these that you start to kind of throw out because you just don't run into them. Anyhow, I should get going because I have an office hour in 3 minutes. You guys have a wonderful day and be wonderful human beings.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.